Hey there, it's Shannon Math Chick Myers, and today we're going to be looking at section 14.5 from the Larson and Edwards calculus text. So today we are working on surface area. So our goal is to be able to use a double integral to find the area of a surface. So let's warm it on up by finding the area of the parallelogram with vertices. A equals 2, -3, 1. B equals 6, 5, -1. C equals 3, -6, 4. And D equals 7, 2, 2. So this was way back when in chapter 11, section 11.4. So if we just take a look at the picture, you get something along these lines. Okay, so there's the picture of our parallelogram, and recall that the area of a parallelogram is the cross product of adjacent sides, okay, where U and V, those vectors are adjacent. So, let's see, we can use CD and AC for our adjacent sides. So if we do AC is equal to U, that would end up being the vector, what's that, 3 minus 2. -6 minus -3, and 4 minus 1, which is 1, let's see, -6 plus 3 is -3, and then 3. And then if we use CD as our V, we would get 7 minus 3, 2 minus -6, and 2 minus 4, which gives us 4, 8, and -2. Good so far? All right. And so, first finding U cross V, we will get the determinant I, J, K, 1, -3, 3, 4, 8, -2. And then that's going to be equal to, let's see, I'll just expand about I, J, and K, so plus, minus, plus, so we'll get negative, which determinant will we get? We'll get 24 minus 6 times I minus negative 2 minus 12 times j, and then plus 8 plus 12 times k. So that would give us 18i plus 14j Oh, and this should have been, these should be switched. So this would be negative 18i. Sorry about that. All right, and then 20k. So the area will be the magnitude of that vector. So our area will be I don't know, we can take a 2 out of each of them, can't we? So we would get absolute 2 times the magnitude of negative 9, 7, and 10, which would give us 2 times the square root of 81 plus 49 plus 100. So our area will be 2 root 230, and let's see, I'm not sure if that can be reduced anymore, but let's just go ahead and call it that. That's in square units. Cool, cool. All right, so now the reason we did that as a warm-up is because we're covering surface area. So if f and its first partial derivatives are continuous on the closed region R in the xy plane, then the area of the surface S given by z equal to f of x and y over R is given by the double integral of that region with respect to S, all right, being the surface S. And so you get the double integral over the region of 1 plus the first partial derivative with respect to x squared plus the first partial derivative with respect to y squared, and that's all under the square root, and then dA. So let's look at an example. Find the area of the surface given by z equals f of x and y over the region R. So f at x and y is 15 plus 2x minus 3y. All right, so our region is the square that has vertices 0, 0, 3, 0, 0, 3, and 3, 3. So here we go. So our region will be like this: 0, 0, 3, 0, 0, 3, and 3, 3. So we've got our square. So there's our region, and then we'll make it vertically simple. All right, and so it's going to look something like this. All right, so here we go. We have let's find our partials. So fx of x and y is equal to 2. Fy of x and y is equal to -3. And so the area, I'm going to say surface area, the surface area is equal to, in general, the double integral over the region of the square root of 1 plus fx at x and y, plus, and that's squared, plus fy at x and y squared, and then with respect to a. So for us, that will be both x and y, do you see, would be moving from 0 to 3. So this first little rectangle represented dx, and if you were looking at the second time, you would, be moving like this for dy. And so we'll have the square root of 1 plus 2 squared plus -3 squared. And then I'll go ahead and do dy dx. So that'll be the integral from 0 to 3 of the square root of 1 plus 4 is 5 plus 9 is 14, which, don't let it confuse you, it's just a constant. So we will get the integral from 0 to 3 of root 14 times y, evaluated from y equals 0 to y equals 3. And so we will get the integral from 0 to 3 of, the lower limit will zero out, so we'll just have 3 root 14 dx. So then we'll get 3 root 14 times x, going from x is 0 to x is 3. And then again, that lower limit will zero out. So at the end of the day, we will get 9 root 14, and that's in square units. Cool, cool? All right, so let's look at our next example. Let's go ahead and find the area of the surface given by z of x and y over the region R. So if we graph our region R, all right, we've got, let's see, the inside of a circle, right? Inside of a circle and including the edge of the circle. So if this is 1, 2, 3, 4, 1, 2, 3, 4, 4, 4. All right, gotta love technology, huh? So our region, whoops, is in here. Okay, so setting up my integral, let's see. Oh, first let's do what's fx of x and y. Beautiful. It's just x. Nope, sorry, it's y. And then fy at x and y is x. So setting up our integral, our surface area would be Now, if I do dx at the very outside, x is going from, beautiful, -4 to 4. Y would be moving from, if I was isolating y and writing it in terms of x, do you see it's a circle with radius 4, so it'd be root 16 minus x squared at the top and negative root 16 minus x squared at the lower limit. And then my f of x and y, I found my partials, so I'm going to have the square root of 1 plus x squared plus y squared dy dx. Cool so far? Well, and actually to do it exactly in order, it would be 1 plus y squared plus x squared. But this might be a lot easier, right, this might be easier to use polar coordinates, right? Or switch this in terms of polar coordinates. So let's check it out. My surface area would be, so if I'm using polars, x squared plus y squared, remember, is r squared, right? R squared. And so my integral would go in the order of dr d theta, right? So r would be moving from, remember, you're looking at circles going around, r would be moving from 0 to 4. And then we'd have the square root of 1 plus r squared from our radicand, or not radicand, our integrand. And then we have another r from the conversion formula from polars. This is going to be dr d theta, and theta is going in a full circle, right? So you've got 0 to 2 pi. Cool? Now, in order to integrate, my g would be 1 plus r squared. G prime is 2r. So I need a 2 in here. So I'll multiply by 1/2 on the outside. So my surface area will be 1/2 times the integral from 0 to 2 pi. And then integrating, I'll get, what's that going to be? 1 plus r squared, all raised to the 3/2. So I'll have 2/3, 1 plus r squared to the 3/2. Going from r is 0 to r is 4. So my surface area will be, let's see, the 2's divide out, so I'll get a 1/3 integral 0 to 2 pi's. And then plugging in my 4, that would be what, 17 to the 3/2. And then when I plug in 0, I'll just get -1 to the 3/2, which is 1. And then I'm still integrating with respect to theta. And don't worry if it's an ugly number, that's okay, it happens sometimes. So now my surface area shall be 1/3, right, times all of this, which is just a constant, 17 to the 3/2 minus 1, times theta. From theta is 0 to theta is 2 pi. So that will give us, let's see, when theta is 0, so the bottom limit will 0 out. So we'll end up getting 2 pi times 17 to the 3/2 minus 1 all over 3 square units. Cool? All right, so that's our result here. And remember, this was our region R in that problem. This is our R in that problem. And so here we go. Another example. Find the area of the surface. So what we're looking for is the portion of the cone, z equals 2 times the square root of x squared plus y squared. Inside the cylinder, x squared plus y squared is 4. So let's check that out. Our region R is going to be that circle. So the circle with radius 2 is our region R. So this would be, I'll just make it a little bigger if that's 1, 2. So that's X and Y. And so we have our circle. All right. And then our region is here. Our region R. So let's check out what we've got going on. Again, I believe that this again is going to be easier using polar coordinates, looking at what's inside right here. X squared plus y squared is r squared, right? So, but we'll set it up in rectangular and then check it out. So if I set it up with dy dx, the x would be going from -2 to 2, and again you've got the bottom half of the circle when you isolate y, and the upper half, so 4 minus x squared. And we need some info, don't we? Sorry, we need to have our zx is going to be what? It'll be 2 times 1/2 x squared plus y squared to the -1/2, and then times 2x. And that, let's see, these 2's will divide out. So we'll just have 2x over root x squared plus y squared. And then zy will be similar. We'll have 2 times 1/2 x squared plus y squared to the -1/2 times 2y. So that'll be 2y over the square root of x squared plus y squared. So then this will all be the square root of 1 plus cx squared, which will be 4x squared over x squared plus y squared, plus 4y squared over x squared plus y squared. I'm already squaring them. dy dx. But this will simplify quite a bit. So our surface area will be the integral from -2 to 2, the integral from root 4 minus x squared to positive root 4 minus x squared. And then we'll have the square root of 1 plus 4 times the quantity x squared plus y squared over x squared plus y squared. I factored out a 4, and then that's dy dx. And those are going to divide out to be 1. So after all that, we're just going to have root 5. So the surface area will be 0 to 2, and then negative root 4 minus x squared to positive root 4 minus x squared of root 5 dy dx. So now I want to put this into polar just because the limits of integration are kind of mean. And so let's see what happens. We will get our surface area is, I'll bring out that root 5, and then our theta will go from 0 to 2 pi. And then our r goes from 0 to 2. And we have an r from the formula, dr d theta. So our surface area will be root 5 integral 0 to 2 pi r squared over 2 from r is 0 to r is 2 with our d theta hanging out, which will give us the 0 will 0 out, and then r squared would be 4, and then over 2 we'd have 2. So we'd get surface area is 2 root 5 times the integral 0 to 2 pi d theta. So we will get 2 root 5 theta, and that's from theta is 0 to theta is 2 pi. And we will have, let's see, I think 4 pi root 5. Does that look okay? 4 pi root 5 square units. Awesome, awesome. All right, and then our last example for the day, we just need to set up this integral, okay? So we want to set up a double integral that gives the area of the surface on the graph of f of x equals e to the negative x sine y, and then our region is x and y such that x is bound between 0 and 4, and y is bound between 0 and x. So if we have, let's see, 1, 2, 3, 4. 1, 2, 3, 4. So here's our x and here's our y. And so x goes from 0 to 4, and then y goes from 0 to x. So we would have the line y equals x, and then we'd also be bound here and here for the other bounds. So that gives our region right here. So let's do it. Let's get our partials first. So fx of x and y, we've got a no product rule on this because the sine y will be treated as a constant. So we'll get negative e to the negative x times sine at y. Just love partial derivatives, don't you? And fy of x and y will be, let's see, e to the negative x times cosine at y. Cool so far? Okay, so now let's do our square root stuff. We'd have 1 plus negative e to the negative x times sine y quantity squared plus e to the negative x cosine y quantity squared, and that's going to equal to the square root of 1 plus positive e to the negative 2x sine squared y plus e to the negative 2x cosine squared y. because you would get e to the negative x squared, and so then you multiply the powers. So that, if you factor out an e to the negative 2x, you're left with sine squared at y plus cosine squared at y, which is what? Beautiful. 1. So you'll have 1 plus 1 is 2. Or no, sorry, not 1 plus 1 is 2. It'll be e to the negative 2x times 1. So this is going to give us root 1 plus e to the negative 2x. Cool, cool? All right. So now our limits of integration is setting up our integral, which was the whole point. We're going to get, that was all our prep work. So the surface area will be, if I'm going dy dx, then remember y is moving from 0 to x, and x is moving from 0 to 4. And so we will have the square root of 1 plus e to the negative 2x, and then we'll have dy dx. Cool, cool? All right, so that was our job for this problem, and next we'll be looking at triple integrals and applications. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show, and if you like what I'm doing, hey, please subscribe and tell all your friends. Bye.